Chapter 3: The Weight of Information, How Mass Emerges from Entanglement. Let's take a quiet walk through the forest of fundamental physics. Imagine we're standing in front of a massive boulder. You try to push it. It doesn't budge. Why? Because it has mass. Mass is resistance to movement. But if we press further and ask, why does anything have mass in the first place? We enter territory far stranger than any forest trail. For centuries, mass was taken for granted, a given, like color or smell. Newton didn't question its origin, he just worked with it. Then Einstein showed that mass and energy are interchangeable, but still. He didn't tell us where mass comes from. In modern physics, the Higgs field is said to give mass to particles. Like a kind of cosmic molasses. But RUEQFT, the Renormalizable Unified Entanglement Entropy Quantum Field Theory, dares to ask a deeper question: could mass be a shadow of information itself? To see how this works, we must venture into the invisible. Every particle in the universe is surrounded by a haze of uncertainty, a quantum fog. This fog is where entanglement lives. It's the glue that binds together distant particles. The whisper between atoms even when they're miles apart. In RUEQFT, this fog isn't just a side effect, it's a fundamental player. And when a particle forms, when a field settles into a particular configuration, some of that entanglement must collapse. A decision is made. And that decision, that loss of entanglement, has a cost. That cost is what we feel like mass. It's a little like a stretched rubber sheet. The more you pin it down, the more structure you impose, the more tension you introduce. In the same way, when a quantum field selects a configuration and loses part of its entanglement with the rest of the universe, it's like pinning down part of that rubber sheet. Energy is stored. The field becomes heavier. That's the origin of mass in the RUEQFT picture, not from collisions or vibrations, but from the reorganization of information. This is a radical idea. It says that mass isn't a thing you start with. It's a price you pay for structure. And that price is measured in lost entanglement, a kind of entropy collapse. More precisely, when the entropic potential of the field changes, the field resists. It pushes back. That resistance manifests as mass. Let's make this idea even more vivid. Imagine you're trying to build a sandcastle. The grains want to stay loose and free, that's the entangled state. But when you mold them into towers and walls, you reduce their freedom. You impose order. And to do that, you must push. That push is the cost of collapsing possibilities. And that's what mass is, the resistance of reality to giving up its entanglement. But mass is only half the story. In the previous chapter, we learned about damping, the fading away of a wave or fluctuation. We learned that the damping rate, omega, is tied to how information flows through the system. Now, RUEQFT tells us something extraordinary. Mass and damping are not separate effects. They are two sides of the same informational coin. The theory shows that as a field becomes heavier, that is, as it loses more entanglement, it also damps more quickly. The equation looks deceptively simple. Omega is proportional to m raised to the power of 2 plus delta eta. But behind this formula is a profound truth: the faster a structure is born, the faster it begins to decay. Because the flow of information is always trying to rebalance itself. This is not a poetic metaphor. It is something we can measure. In experiments at particle colliders and in cold atom labs, we can observe how particles decay. We can see if their damping rates follow the new scaling laws predicted by RUEQFT. And if they do, then we will have uncovered something astonishing. Mass and decay are linked by a universal informational flow, just as energy and mass were linked by Einstein. This chapter brings us to a point of reflection. What if everything we think of as material mass, inertia, resistance, is just the visible result of invisible information currents? What if the solidity of the world is just a local slowdown in the universal dance of entanglement? In RUEQFT, mass doesn't exist in isolation. It's not a gift from the gods or a particle from a hidden field. It's the footprint of a deeper process, the dynamic interplay between a system and the entangled universe around it. And damping the fading of excitation is not the end of something. It is the system's whisper back to the universe. I am giving back what I once borrowed. In the next chapter, we will explore how this entire framework, this intertwining of mass, entropy, and damping, fits into the powerful machinery of renormalization. and how it allows us to make real, testable predictions about the universe. But for now, remember this: in the world of RUEQFT, mass is not weight. It is memory, a record of choices made, of entanglement lost, of the universe organizing itself one field at a time. Chapter 4: A Universe in Flow, Entropy, Time, and Thermodynamic Relativity. Imagine sitting by a river. The water flows smoothly, guided by the shape of the land. Now imagine that same river winding through mountains, then flatlands, then over cliffs. Depending on the terrain, the river's pace changes, sometimes a trickle, sometimes a roaring rush. Now imagine that what flows isn't water, but information, in the terrain it flows through isn't land, but time and space itself. This is the central metaphor of RUEQFT's fourth chapter. The universe is not only made of matter and energy, but also of flowing information. And just like rivers carve valleys, the flow of entropy, a measure of informational spread, reshapes the dynamics of everything that exists. To understand this, we need to look at how entropy becomes a force of its own. In traditional physics, entropy is often treated as a side effect. Something increases when things go from order to chaos. A hot cup of coffee cools, a broken vase stays shattered. But what if entropy wasn't just a background statistic? What if it were an actor in the play? RUEQFT proposes that entropy, especially in the form of entanglement entropy, has direction. It can flow. And when it flows in time, we feel that as change. When it flows through space, we see that as structure. When it flows unevenly, say, faster in time than in space, it creates what the theory calls anisotropy, a difference between how a system responds over time versus space. Here's where things get intriguing. Imagine two people, Alice and Bob, watching the same experiment. In the old world of Einstein's relativity, they could disagree when something happened if they were moving differently. But now, in this new informational worldview, Alice and Bob might also disagree on how fast a system returns to equilibrium, not because they're moving, but because the entropy itself flows differently in time and space. This leads us to a concept called thermodynamic relativity. It's a bold idea, just as special relativity taught us that time can stretch and contract depending on speed. Thermodynamic relativity tells us that the rate at which systems relax, how quickly they settle into stability, can stretch and change depending on how information is flowing through them. And this change is captured by a deceptively simple quantity called d delta eta, the difference between the anomalous scaling of time and space. When d delta eta is 0, time and space are balanced, and the system behaves classically. But when d delta eta becomes positive, something fascinating happens. The system resists change. It takes longer to relax. It's as if the universe itself says, "Wait, I'm thinking." This extra time isn't just philosophical. It shows up in real, measurable ways. Physicists describe how quickly a system settles by something called the dynamical exponent, usually denoted z. In standard theories, z equals 2. But in RUEQFT, this changes. It becomes 2 plus d delta eta. That small extra term, a whisper of entropy imbalance, creates measurable effects. It changes how ripples fade in particle detectors. It alters how critical points behave in materials. And it even stretches the notion of now. Let's take this further. In Einstein's relativity, we have something called the Lorentz factor, a number that tells us how time dilates for someone moving close to the speed of light. In RUEQFT, a new factor emerges. Gamma gamma th, the entropy flow Lorentz factor. It tells us how time stretches not because of speed, but because of entropy. And it's defined in terms of the correlation length of the system. How far the system's influence reaches. As this length grows near a critical point, as systems become interconnected, gamma th grows too. Time itself dilates under the weight of information. This is no longer just about particles. This is about the pace of becoming. About how a system knows it's changing, and how the universe respects that knowledge. The laws of change, of transformation, are no longer fixed. They evolve with entropy's own flow. One might ask, what does this mean for us? It means that our universe may not be governed only by energy conservation and spacetime geometry, but by a deeper river of information whose currents define how fast reality rearranges itself. When d delta eta is positive, change slows. Information lingers. The memory of a system, its resistance to forgetfulness becomes tangible. In a world built on RUEQFT, the speed at which things happen depends not only on forces and masses, but on the pattern of information. This is a universe where memory is motion, and entropy writes the rules of time. As we close this chapter, we begin to sense something profound. The universe isn't just expanding its thinking. Every collapse of a quantum wave, every decay of a particle, every phase transition in matter, all these are steps in a larger informational choreography.